All right, I think we'll get started today. So hi, everyone. Happy Friday. I'm Natalie, Irwin, Director of Stakeholder Engagement here at Efficiency Canada. I'm located in Ottawa, Ontario, which is the unceded territory of the Algonquin Nation. But we do have staff all across Canada. Welcome to another discovery session. Before we get started, a reminder to everyone that our guest speaker will present for approximately 20 minutes today, and then we'll open the floor to questions. Please use the Q&A box at the bottom of your Zoom screen, and we'll wait until the end until we get to them. If you want to type questions throughout the presentation, that's fine, but we won't get to them until the end. You can also raise your hand and I can unmute you. And if you're brave enough, you can ask your question yourself. We do have a hard stop at 12:45 p.m. Eastern time so that everyone can finish their lunch, breakfast, afternoon snack, depending where you are in the country, or countries as it may be in the case of today. So without further ado, I'm pleased to welcome our guest speaker today, Philip Johnston of Daikin Applied Americas, who's joining us from the US today, who will speak to the future of refrigerants. Please join me in welcoming Philip. Thanks, Philip.
You're welcome. Thanks for having me. Well, I guess I'll get started. We got a few minutes here and I'm going to race through some slides. Yes, I do work for Daikin Applied Americas, and you'll notice here I'm a professional engineer, which tells you, guess what? I'm probably from Canada. And yes, I grew up in Ontario, in Haliburton, moved to the States, did a big left-hand turn and got out of chemical engineering and went into air conditioning, and basically worked my way up through the ranks at McQuay, now Daikin Applied Americas. And for the last 2.5 years, I've been basically leading Daikin Applied's transition to low GWP refrigerants. So really, we're talking about air conditioning here, and that's what I'm gonna go through. I'm not going to talk too much about legislation or regulations. I'm just going to dabble in that and probably talk about what you're going to see in the future. I think the big thing that I'm trying to show with this screen, and this is just some of the announcements, is there has been an awful lot of announcements about which competitors around the world are going to use which refrigerants, whether it's to replace 410A, 134A, R123 and chillers, residential, light commercial, ducted, non-ducted. And so there's a lot of information out there. And we're going to sort through some of that and tell you what you should expect. So the way I've set this up is sort of a Q&A session. You don't have to read through all of this due to time. You're going to see this slide several times. So this is my understanding of relevant Canadian regulations, and that is that Environment and Climate Change Canada quite a ways ago has set up some regulations, but really it's all around chillers in the world that I'm in the industry that I'm in. You need to be less than 750 GWP by January of 2025. Not aware of any regulations in Canada yet for direct HVAC systems. So your traditional residential, light commercial. So it makes me wonder, is Canada waiting for alignment with the USA with their HFC phase downs? Very briefly, California has been the de facto leader, and you'll see some other states here because these are the US Climate Alliance. There'd been a vacuum for 4, 5, 6 years where nothing was really happening in the United States. So these states decided to move. And California has also set a limit of 750 GWP with these key dates that are on the screen for these sorts of air conditioning applications. The other states tend to be following California, but waiting for the US to do something. And boom, it happened. So last December, so almost a year ago, US Congress, jointly, Republicans, Democrats, and the President Trump signed the AIM Act as part of a very large packaged bill. And basically it aligns with the Kigali Amendment. Very briefly, I will say EPA must then write regulations. And there's two ways, in the basic piece of it is, if you're going to do the Kigali Amendment and the AIM Act, they phase down both production and consumption of bulk HFCs. And the current regulations EPA drew up just cover what's going to happen next year and in 2023. The second thing down below is it allows the EPA to take petitions from anyone. They call them sector-based petitions. And the EPA, and there's been 13 that I'm aware of that were submitted. And basically the EPA has decided they will write regulations around some of these petitions. And an example of a petition would be, hey, California, or CARB, the California Resource Board, wants to transition direct air conditioning for, I'll say VRF on January of 2026 or chillers January of 2024, please line up with what California is doing and be consistent across all the United States. And you know what? The EPA is going to consider that. And they have up to 2 years to make those decisions. But that's what's going on down here. Fact of the matter is it's happening in the United States. It's happening in Canada, but it's not completely clear what's going to happen in Canada at this time. So what's the myth about global warming potential? You will hear a lot of people saying GWP is everything and it's the most important thing. And I'm here to tell you, it isn't the most important thing when you're talking about climate change. It is a piece of the issue and a significant piece of the issue. There's no denying that. In most parts of the world, the single largest contributor to climate impact in terms of air conditioning equipment over its lifetime is actually the indirect effect. In the United States, it's 80 to 90% because most of the electricity is produced from the burning of fossil fuels. So efficiency matters. It is a really big deal. The performance of your refrigerant and the performance of your equipment and your building designs matters. It's 80 to 85%. Let me show you a real world example. This is again in the United States. So the indirect effect from electricity consumption is the dark blue bar. And you can see that if you move to R32 from R410A, and R32 is a lower GWP refrigerant, you can reduce the size of that blue bar by a few percent because it performs better than R410A. But the other point is that is the blue bar is the single biggest piece for this model, which was all residential lifetime equipment across all the United States. Okay. When it comes to the GWP of the refrigerant, that only happens from leaks. It's leaks, and it's called the direct effect, whether it's leaks at end of life or leaks during operation. And you will see leaks during operation is the light blue gray bar. So certainly if you go from a GWP of over 2,000 per pound of refrigerant, down to under 750 GWP, and with R32, 675, you're going to see a reduction of that blue bar. So what we're really dealing with when it comes to the change of the refrigerants is dealing with that light blue bar and the orange bar. But on the other hand, if you start using a refrigerant that isn't efficient and you raise that dark blue bar, that's going to hurt you as well. So you don't want to do that. So we've heard about another refrigerant, and it will be used, called R454B. A number of HVAC manufacturers have decided to use it to replace R410A, but not all of them. And in fact, what I will say is the Carrier has decided, and JCI, and I think Rheem, to use R454B in some of their ducted equipment, but not necessarily in all their chillers. Carrier is using R32 in some of their chillers. I think the chemical producer for R454B, it's a proprietary blend of two different chemicals, is stating the benefits are the lower GWP because it's under 500, but it's also being touted as having very similar performance to R410A. And I think having similar performance to R410A is really good for a manufacturer because it's less design work when redesigning the equipment. But what we're really trying to accomplish is really with regard to climate change, and we want to know, what do our customers want? Do they want better performing equipment or status quo? The other thing to remember too is GWP itself is not really part of the Kigali Amendment. It is as a direct measure. What the Kigali Amendment is doing is summing up the use of HFC refrigerants, and so total mass times the GWP from every HFC used in every sector across the country, and summing it to total CO2 equivalency. So a refrigerant with a slightly higher GWP, but maybe you can use 40% less because it performs so well, might be better than a refrigerant with a slightly lower GWP, but you're using more of it. So there's some math involved there. But you're going to see R454B by a number of manufacturers out there. Now, R32 is the backbone of all the refrigerants. I'm going to show you some data here. It's already being used around the world as early as 2012 as a pure single component refrigerant. But remember, R32 is also 50% of R410A. So it's the backbone for R410A. There's over 160 million units. used by over 40 different manufacturers in over 100 countries right now through this year. So it is out there in chillers, water source, VRF, mini splits, multi splits, window air conditioners, even here in the United States and probably Canada. If you go to your home store and look at a window air conditioner, it might have R32 on the data plate already. And that's because the charge levels are so small, manufacturers have already moved to it. Some of them have. So why are they using it? Well, as an alternative refrigerant, a single component refrigerant is so much easier to use than a blended refrigerant. It's much more easily manufactured. Right now, because it's 50% of 410A, there's already over 200 million pounds being used and manufactured around the world. So really, you only have to roughly double production to get to what you need to satisfy the current customer base. Whereas some of the proprietary refrigerants have special chemicals in them that they need to spend hundreds of millions of dollars to build plants. Very important, it's not restricted by any patents. This is a non-proprietary basic single chemical available pretty much from a number of manufacturers, manufactured in the United States, India, Japan, China, other places, okay? Imagine Kigali Amendment says, you know, they're setting allocations and limits for the production of virgin bulk refrigerants. So imagine if you just reused everything that you had today. We've been taught since we were children, at least my generation, reduce, reuse, recycle. With a single component refrigerant, you can do that. And very little refrigerant today is being reclaimed. But in this future world, we need to create a circular economy around using reclaimed refrigerant. That is much, much easier when you have a fairly stable refrigerant in a single component because the blend compositions aren't going to change over time. It's a simpler process for reusing them. Let's talk performance. This was a third-party NIST generated and third-party reviewed paper that came out that compared efficiency on the vertical axis to 410A. So all these efficiencies were normalized to 410A, and volumetric capacity. So capacity and efficiency tend to be the most important things when you're comparing refrigerants. And in this study, they were comparing just single component refrigerants to R410A. So if a single component refrigerant performs better in terms of capacity and efficiency than 410A, it'll be in the top right-hand column. So there's only one refrigerant out there that is known to perform better than 410A in a single component, and that's R32. That is why it is the backbone for everything out there. And it just happens to be fairly low GWP. With blended refrigerants, if you were to blend them together, you're gonna, and if R32 is the backbone, you know that you're gonna fall somewhere in the middle. So this other refrigerant called 454B does perform similarly to 410A, but with slightly less capacity. So similar efficiency, slightly less capacity. And that's because they're blending in 61.1% of this R123YF, which is an ultra low GWP refrigerant that is at about a 95% efficiency point. Okay. So no matter what, it's going to fall somewhere down around 410A. So you're going to lose that benefits of the R32 performance using that refrigerant. What does that look like in terms of some testing? This is from actual test in the lab of an inverter rooftop unit, where it was set up with a 410A, which is the standard, put in an R32 compressor and ran the inverter at the same number of RPMs. So the compressor at the same number of RPMs, and it actually put out a lot more capacity. But then you realize, well, it's a nominal, say 10-ton unit. To put out 10 tons with R32, you could run that compressor a lot slower. And when you run the compressor a lot slower, you consume a lot less power. So what we saw is an IER improvement of 10% in that particular unit. It was really cool to see that. 10% efficiency improvement is huge in terms of operating your building and in terms of life cycle total climate performance. Then we removed the R32 and we put in the 454B. And when we ran at the same RPMs as 410A, it lost capacity. So we had to speed up the compressor, which is possible with inverters, to achieve nominal capacity. So it was consuming more watts, and we lost about 5% efficiency using 454B. So just interesting real data points from some real equipment. So In summary, comparing 454B to R32, you can see that they're both A2L refrigerants. They both have room concentration limits, which is part of, ASHRAE 15 standard and the UL standards for how you apply these refrigerants that are about the same. So they have a similar amount can be used within the space. You can see 454B has glide of about 1.5 kelvins degrees Celsius. Yellow means to me similar efficiency to 410A, the incumbent, but less capacity, so it's red. But the cool thing about R32 is it's green for both efficiency and capacity. It's better. The only knock against a big difference here is the GWP of 675 for R32, but 454B is at 466. But the pretty cool thing about R32 is because it performs so well, you're going to be able to use 20 to 40% less refrigerant within your system, whether it's a self-contained unitary product or even a residential split system, than R410A. So I talk about effective direct GWP. And I do that because of the allocation rule. Like, what really matters is how much are you using and what's its GWP. So effectively, it has an effective GWP closer to 475. Pretty cool refrigerant. So what's really awesome is you can move away from 410A and actually get better performance, potentially improved operating costs over the life cycle of the equipment as well. So there's another option out there. There is a refrigerant that is not commercially available anywhere in the world called R466A that's getting some study, and it's called and it's actually been decided as an A1 in ASHRAE 34. Let's talk about that. It's actually a 3-component blend. So we've never seen a 3-component blend before. Again, the backbone is still 49% R32, 39.5% CF3I, and then 11.5% R125. And this is a super high GWP refrigerant. It means that it's got a higher GWP, but still below the 750 threshold. Because it doesn't perform as well, you need more charge, pulls you up to around an effective GWP of about 800. Room concentration limit. This is what's interesting. Even though it's an A1, it has an RCL that is quite similar to R32 and 454B. It's still, only about 25% of what the RCL is for 410A. You got to ask yourself, well, why is that? Well, the chemical producer designed in just enough of this proprietary blends to squeeze into the A1 category, like to pass the non-flame propagation tests. But it still has a fairly low RCL because of the toxicity of those particular components. So it comes with glide, slightly lower performance than 410A, but similar. So reds, and then there's questions about the stability. And when you look at the stability, you've probably never heard of the refrigerant GFCI. And what you've got is a carbon iodine bond. Most bonds within refrigerants are these fluorine atoms, but iodine is still a halogen in the same column of the periodic table, and it's a weaker bond. When that happens, it's been shown in the Kobe Symposium as early as 2018, and several reports and papers after that it can break down in higher temperature applications. That in turn results in the formation of acids within the system. So the question is, how can we ensure that this refrigerant can remain stable within typical applications of HVAC? And that's unclear right now. The chemical producer and this one OEM looking at it have said that the secret proprietary additive formulation that the producer has come up with within the oil can prevent the breakdown into acids, and also scavenge the acids when they're formed. And most of us don't know what that means. So I would also say that that OEM published some data that the life cycle, these additives don't even work at a standard industry life cycle test condition that all the refrigerants we're using today will pass. So even with the additives, I have some concerns. We're also not aware of any major compressor manufacturers developing compressors around this refrigerant. We don't know, will it cause corrosion within vacuum pumps or charging stations, let alone the equipment. So we don't know what's going to happen with the life cycle of this refrigerant. It doesn't seem to be getting any traction, and certainly it's not available in any production quantities of note today, but it is being discussed. So the primary concern here is, three components, highly proprietary, and the stability factor. So in summary, looking at some of the replacements, we see 410A there with the A1. We've rolled in the three major refrigerants that are being discussed. I think for sure you are going to see pure single component R32 being used in the market today in North America, whether it's from those 40 manufacturers when they start importing their mini splits and VRFs into North America. We're also Daikin using R32 in our products because we've made that announcement, whether it's Carrier who's announced the use of R32 in their chillers, and then 454B, several manufacturers have announced using that as well to replace 410A. So that's just a decent summary page for all of you to look at. So let's talk about chillers in some of the time remaining. There's a refrigerant out there that if you're working on chillers and looking for low GWP refrigerant options to replace 134A, there's a blended refrigerant called 513A. And I get asked, is that going to be the long-term replacement? And my answer is no. It's more or less an interim replacement. And that's because if you look on that right-hand side on the chart, you'll see that it loses about 3-4% efficiency, but almost identical capacity as compared to 134A. So this is another example of a refrigerant that has been blended particularly to match up with 134A performance to make a manufacturer's life easier. And it happens to be an A1 refrigerant, but it has a moderate GWP level of 631. And it's made up of 44% R134A. So I think this is good in certain markets where customers are demanding lower GWP refrigerants by policy, or perhaps where electrical power is very renewable, so people might care less about efficiency. But efficiency still matters, let's face it, right? So, I mean, we're talking to Efficiency Canada, so I don't have to tell you, but I would say that I don't think this is going to be the long-term play. There is another option out there. There's a pure single component refrigerant called R123 has an ultra low GWP. It's not just Daikin that has used some of this in their chillers. It's being used by a few other manufacturers around the world. It has, I'd say, slightly higher efficiency than 134A, but you lose about 25% capacity. So you would need to use slightly larger equipment than what is going on with 134A. Now, it also happens to be a group A2L refrigerant. So the refrigerant producer came up with this blend called 515B. So if you look at the second bullet, that's 91% R1234ZE, and then they blended in 9% of another refrigerant so that they could pass the A1 test. So what you're seeing here is innovation and in the creation of proprietary blends where they're trying to change the properties to get lower GWP refrigerants, but also try to squeeze into the A1 category. And you've seen examples of that with the 410A replacement. This is an example of that with the 134A replacement. The GWP, when you do that, goes from 1 up to 292. So I think what we're going to see emerging out there in the market as we transition is the use of 1234ZE or that blend 515B to replace 134A as well. So in summary, this is the summary chart. I actually believe that 134A is an excellent value today for any A1 refrigerant. But if you're looking to go to a lower GWP refrigerant, and if you want it to be an A1, you're going to have to move to 513A or 515B. And then ultimately, if you're okay with an A2L in your mechanical rooms, then you can go with 1234ZE. Either way, there isn't a double green to replace 134A, and that's too bad. No matter what, you're losing something on efficiency and or capacity to move away from 134A. but there are options there, and you're going to see them if you haven't seen them already. So there's also to replace R123. You can't use R123 anymore because of its ozone depletion potential, but there is a manufacturer using 514A, and we wonder what's all about that. Well, 514A is has very similar performance to 123. It's another blend, but it's a blend without glide of these two chemicals in the first bullet. Ultra low GWP, so that's really good. And I think it's a non-ASME type chiller design. So that particular OEM can probably retain use of much of their R123 designs. It is only one manufacturer using it. Most chiller manufacturers have moved to another refrigerant. So it might be expensive, but I don't know for sure. It retains the toxicity classification of a higher toxicity B, and that's identical to 123. So I hazard to guess that if customers or engineers are okay with R123's higher toxicity B status, they're probably okay with this refrigerant as well. There is another option on the left-hand side here, and it is being offered by all four major chiller manufacturers, and it's called R1233ZD. The cool thing about that is it's got the class A1 rating, and it's also an ultra low GWP. The cool thing is its efficiency is pretty good too, very similar efficiency to 123, but it has slightly improved capacity, and clearly with its A category toxicity of lower toxicity, that's an improvement as well. And I think that's why all the major chiller manufacturers have provided at least some products in the world to use this particular refrigerant, because its performance is pretty darn good and it's a class A1. So I actually think this will be the long-term refrigerant in the larger centrifugal chiller space. It's a pretty good option. So I wonder where else can you get more information this transition, because I had to motor through this. You can go to a number of sites. We have a Daikin Learning Institute to learn. There's r32reasons.com. You can check out daikinapplied.com. More importantly, check out AHRI. They have their Safe Refrigerant Transition Task Force. I did not get into the use of A2Ls and the standards, and they have a ton of information there, and you can learn from them. It's been going on now for over 10 years, and the industry has matured and is ready to go. When it comes to training for technicians, there's training being offered online by the ESCO group at this website, as well as ACA. So training is already available on the use of A2L refrigerants, and you can fully expect when manufacturers come out with their products, whether they be R32 or 454B, we'll be offering training as well. So what did I tell you? This is how I'm supposed to close every presentation. Is I told you a bunch of stuff. How does it summarize? For low pressure centrifugal R123 replacement, 514A is out there available. I believe the class A1 1233ZD will be the long-term solution, and they're available today from in a number of product lines from most chiller manufacturers. To replace 134A, 513A chillers tend to be available today from most manufacturers, and I think 515B or the pure single component version 1234ZE will follow here in North America. When it comes to replacing 410A, I really like the use of R32 because it's that pure single component refrigerant, proven global alternative. It's available, it's easy to work with. You can charge it in the liquid phase, gas phase, and by far it's more efficient across all the applications, which means it's really good for the environment over its life cycle, and it's a very good choice for life cycle operating costs for those who are concerned with that. However, to replace 410A, you are going to see a mixed bag. I mean, for sure in North America, you're going to see R32 and 454B, and we may even see that R466A being offered from some manufacturers. Well, that closes my presentation, Natalie. I can stop sharing if you wish, and I'll turn it back over to you. Thank you.
Sure. Thanks so much. I almost turned it on and I saw you wrapping it up. So I was like, I'll just wait. So you timed that perfectly.
You got lucky.
Yes. So good job on that. No, lucky, well prepared.
Thank you.
So before we open the floor to questions, I'd like to let everyone know that we do record these sessions and post them on our website afterwards. We usually get them up in about 2 weeks' time. You can find them under the education tab on our website. Also, a quick reminder to everyone that we do have one rule, which is the same rule we have for our presenters, and that is no sales pitches, please. So this includes any statements disguised as questions. Again, there are 2 ways you can ask questions. One, people are already typing in the Q&A box. You can also raise your hand and I can unmute you and you can ask your own questions. So let's get started. There's a popular question here from Adrian is, Philip, can you elaborate on the CO2-based refrigeration?
Oh boy.
Quickly.
You're starting to push my comfort zone as a professional engineer to talk about CO2. So anything I say, take it with a grain of salt. I have sat in on ASHRAE chapter presentations where I'm seeing CO2 being used in refrigeration applications, which is not my background. I also know that the Daikin group of companies, at least in Europe, offer CO2-based air conditioning in a sort of piece of equipment where they're producing domestic hot water as well as heat pump heating with air conditioning. And they thought about bringing that to the North American market a few years ago, and for whatever reason decided not to. And I could see it happening in due time. It adds considerable expense to the cost of the equipment, and I believe it is less efficient in operation. So when you think of that GWP method of direct plus indirect equals reality, it may not be the best mix. That being said, I actually predict you're going to start seeing CO2 in niche refrigeration applications. And if it's working in Europe, there'll be a time and a place for it to come and work here as well in certain air conditioning applications. But I just don't know if it'll ever become more broadly used. Hope that helps.
Yeah, I would say so. Interesting. I have a question here from Brendan is, how do they accurately measure refrigerant leaks in national statistics?
I'm not certain that they do accurately measure it. I think that there are calculations done of, we know how much is produced. That's a fact, very tightly understood. There's only 5 producers or something in the United States of HFC refrigerants. Then there's a lot of importers of bulk refrigerants, a couple of dozen, and then there's imported products containing that refrigerant. So I think with the estimates of how much is being produced, they're essentially doing a mass balance on what's coming into the country and out of the country and trying to determine how much is actually leaked. That's how I understand it.
Thank you for that. There's more questions about that further down, but I'm just going to get to a question actually here from Joshua. He says that a contractor mentioned to him that we may be moving to propane for a refrigerant. Any comments or thoughts on this at all?
Yeah, lots of comments. It's a great question, because if we were to go back to that slide, you can go back and look at that performance slide that NIST, you'll see propane R290 on there. And you're going to see that it's pretty efficient. Similar capacity to R22. Clearly must be low cost because it's propane, right? Non-proprietary. So it's not a bad performing refrigerant. It doesn't perform as good as R32 in terms of its capacity. And certainly it's an A3, which means highly flammable in ASHRAE 34. The question is, can we manage its use? And I would say broadly, right now, the industry is not ready to do that. The industry is now ready to move to A2L refrigerants, which are drastically less flammable than an A3. And I could, in some of my other presentations, I can show you, the chemical variables or stats that would demonstrate that statement. But here's some data points. In appliances, we are seeing the use of propane or isobutane in small, like in refrigerators and freezers. They have become standard. And that's because the charge level is very small. It's in grams, right? So they're considered safe because they're self-contained unitary appliances using highly flammable refrigerants, and they work great. So I could see propane, just like in Europe, where it's being used in very small air conditioning systems with very low charge, being used, like window air conditioning, for instance. The question is, are we ready and comfortable using propane in larger systems? And how do we design our, not just the equipment, but the application, the building envelope itself to use an A3 refrigerant? Anyway, that's kind of my take. You're going to start, you will see it eventually. The question is when, where, how niche will it be?
Exactly. That kind of leads to this question from Betsy is, what are the implications of wider R32 use for HVAC techs for maintenance, for first installation or commissioning?
Good question. I will say this. Because it's an A2L, there are a couple of things that you need to be concerned with. However, pretty much all the same practices that we suggest when evacuating, charging R410A should hold with any A2L like R32. I would say there are several benefits of R32 because it is a single component refrigerant to a service tech or an owner of a building. And that is you can charge it in the liquid or gas phase. So if you're coming in with a bottle, that bottle can be sitting there and you can charge off the top of it, and you know you're getting the right mix of components. Whereas a blended refrigerant with glide should really be, the bottle should be upside down and be charging that way. That's really cool. You know that if you've had a leak of a pure single component refrigerant, you can top it up and the composition has not changed. Whereas with blends with glide, you can have fractionation and you could change the blend composition, which could impact performance. So there are several benefits to a tech choosing a single component refrigerant. So I can answer it that way, or I can answer it based off of the A2L side. And I will say that, so if you're following good standard practices like it for an A1 refrigerant, you're not going to see a lot of issues with an A2L refrigerant. That being said, if you are a tech, when your manufacturer comes out with R32 or 454B, they are going to train you. Number one. Number two, I would encourage you, go look at the ESCO group training and the ACA group training that's available right now, and take that training and learn for yourself the specifics and the best practices that you should know about handling and using an A2L refrigerant for your future work, because it's coming.
That's good to know. I'm just curious, does Daikin have anything on you mentioned the Daikin learning portal, I guess, that you have?
We do not have any training yet at the Daikin learning portal to use A2L refrigerants for our contractor customers, because we are not selling any products yet. So there's no training there just yet. So that's why I would encourage you to go to the ESCO group or ACA at this time.
Perfect. Thank you for that. A question here is, what are the implications for different refrigerants in cold climates? For instance, are CO2-based refrigerants potentially better in cold climates? You mentioned you are Canadian.
Yeah, I am a Canadian, yes, but I also live in northern Minnesota, and I suspect the latitude of where I'm sitting today is north of Ottawa. I bet it is. I'm just gonna go. I should go check that. I know I'm north of my hometown in Halbert, so I call my mom and say, "How is it down south?" when I talk to her. I can't speak to CO2, but I would say the use of heat pumps is going to become massive over time. And when you think of the need to minimize climate change, the use of heat pump technology has to start happening in a huge way across all parts of the world that need heating. That brings into the effect of, how do you get the most energy efficient heat pump heating system? And there are technologies and innovation that are required to do that. So a lot of our R&D is focused on cold climate heat pump innovation. How do we drive down, how do we create a lot of heat out of our equipment while operating an air source heat pump in very negative temperatures? So there is a lot of technology there, and certainly there are refrigerants that work better in those environments. And frankly, R32 is one of them because it has such a high latent heat of vaporization. And so it's pretty darn good for heat pumps, which is why it's already being used in Europe by a number of manufacturers in their mini splits, multi splits, whether it's for creating hot air or even hot water being used in radiator systems in Europe. It's kind of becoming the de facto standard over there for that.
Okay, perfect. You actually answered my next question I had lined up for you in that one, so that's great. Love when that happens. Just one more question here is how does/will this affect new home refrigerants, or is this only for large industrial type applications?
Oh, yeah, I mean, great question. I'd say anything where I was talking about replacements for 410A, whether it's moving to R32 or 454B, are directly applicable to residential single family homes, multifamily, and even like, so wherever 410A is being used today, that conversation that I gave applies. So there are certainly ramifications within single family homes when you move to an A2L refrigerant. The first is the product safety standards, and I didn't say this in the deck, and I should. When you go from an A1 to an A2L, it is not a drop-in refrigerant. You will not be able to leave your A coil in your residential unit, like part of your system, and swap out your outdoor unit and go to an A2L. You need a new system. It is a very different safety standard, and it's not UL 1995 anymore. It's UL 6335-2-40, and they're in the third edition allows A2L refrigerants, and the safety design of that equipment is quite specific. Similarly, ASHRAE 15, the 2019 edition, and the to be launched, I think that's the right phrase, ASHRAE 15.2 covers single family homes, covers the use of A2Ls in how those systems need to be designed into the space. So there will be slight modifications to how the systems are designed in buildings when you move to A2Ls as well, that are covered in those standards. So depending on the charge level that is within the system, it changes what mitigations are required within the equipment or the building space to make sure that these refrigerants are safe to use.
Thank you. So just keeping an eye on the time here. I told you how we had a hard stop at 12:45 p.m. So we are there. So thank you so much, Philip, for sharing this presentation on a complex and detailed topic for sure. And you flew through those slides, but you did so with enough detail to give us all kind of enough information. And those who want more, they have various options to find out more. Thank you again for joining us. For those who are joining us next week, actually, I won't be here, but our Executive Director, Corey Diamond, is going to be joined by two of my other colleagues who work in our policy team to discuss this year's scorecard release. So you did hear me correctly. The 2021 scorecard is coming out on Thursday, November 9th or 19th, 18th. So next Thursday, and I am pumped to be on social media that day to see all the tweets and LinkedIn posts, and who knows, maybe we'll get on Instagram or TikTok this year. We'll see. So have a fantastic weekend, everyone. Thanks again for joining us, Philip, and everyone take care. Bye-bye.